Hello, thanks for attending my presentation. My name is Ho-Chan Chang. I am a fourth-year graduate student in University of Wisconsin Medicine. The topic of this talk is catalytic reaction pathways and process synthesis for biomass conversion to commodity chemicals. Over the past 50 years, HMF has been widely studied as a biomass-based platform chemical, primarily to produce FDCA. And FDCA was used for the monomer to produce PEF polymers. So the companies such as AVA, Biochem, and Aventium developed a pilot-scale plan for production of HMF. However, HMF production technology has struggled to become commercialized because of slow growth rate of the PEF market size. Also, there are chemical and technical challenges for HMF production. Firstly, it is difficult to selectively produce HMF in high yield during the reaction. Secondly, we need to develop an economical separation technique to isolate pure HMF from solvent and impurities. For overcoming these chemical and technical challenges for HMF production, we use the acetone water co-solvent system. There are several advantages of using acetone water co-solvent. First, it is non-toxic green solvent. Second, we can maintain the high yield of HMF during the reactions. Third, both solvents are easily evaporated from HMF. The low boiling point solvents can prevent the HMF degradation during the solvent evaporation. Lastly, we can keep the high feed concentration in the acetone water co-solvent, and that improves the economics by increasing the production rate of HMF. Therefore, acetone water co-solvent is suitable for commercial scale HMF production. We investigate its reaction of glucose isomerization and fructose dehydration in the acetone water co-solvent system to produce HMF. After the 40 minutes reaction in presence of the enzyme at 65 Celsius, 61 more percent of glucose was converted to 60 more percent of the fructose. Nextly, fructose was dehydrated to the HMF in presence of the exit catalyst. After the 90 minutes at 120 Celsius, 91 more percent of fructose was converted to 79% of the HMF. We used the reaction temperature and reaction time to synthesize HMF from the glucose by using sequential isomerization and dehydration. The glucose feed in acetone water co-solvent was isomerized by enzyme. The isomerized solution contained only glucose and fructose. Then, the isomerized solution was further dehydrated to produce HMF. Both isomerization and dehydration did not produce much byproduct. However, the dehydrated solution still contains some amount of unreacted glucose and fructose. Therefore, HMF must be isolated from the unreacted glucose and fructose. Chromatographic separation is an excellent method to separate HMF from the unreacted glucose and fructose. For both figures, I used black, blue, and red color to represent glucose, fructose, and HMF. The left figure explains the isothermal adsorption of each chemical on the chromatographic resin. As we can see on the figure, fructose followed the Langmuir adsorption and glucose followed the linear adsorption. However, HMF was not adsorbed onto the chromatographic resin. Thanks to the distinct adsorption behavior of each chemical, we can successfully isolate HMF from glucose and fructose. So we synthesize HMF from the glucose. And then we also developed the process integration strategies to produce HMF. The HMF production process can be integrated with high fructose corn syrup infrastructure. This process integration contributes to low total capital investment by sharing the existing facilities in high fructose corn syrup. As we can see on this table, the minimum selling price of HMF became $1,300 when the HMF production rate becomes 17.5 kilotons per year. This integrated process is the cheapest approach to produce HMF. So I talked about the HMF production from the glucose. However, we need to upgrade HMF to a new platform chemical because HMF has several limitations. HMF has few direct applications, and HMF is too small molecule to undergo various catalytic reactions for various applications. Therefore, currently, HMF has been used primarily for FDCA synthesis to produce PET plastic substitute, such as a PEF. So we need to develop a new biomass platform chemical that has many functional groups and find various applications that having a large market size. Alder condensation has been reported as a powerful reaction to add chemical on HMF. We synthesized the alder condensed product we named HAH as a new biomass-derived platform chemical. HAH has various functional groups such as hydroxyl, diol, furan, enone, and ketone. The selective reaction of each functional group can be used to produce various commodity chemicals. In the next section, we investigate the way to produce HAH from HMF. So to produce HAH, the stoichiometric ratio of acetone and HMF is key feature to control the alder condensed product selectivity. We mix the HMF and acetone in the water with a different stoichiometric ratio and catalyze it by sodium hydroxide. As we can see on this figure, we can selectively produce one alder condensed product, or we could produce the mixture of two alder condensed products. So during the selectivity control by changing the stoichiometric ratio of acetone to HMF, we can maintain the high conversion of HMF, high carbon balance. We also investigated the kinetic model analysis of this two-step alder condensation. The first step alder condensation is between HMF and acetone. The rate constant of the first alder condensation is almost the half of the rate constant of the second alder condensation. Both reactions are the first order reactant. When we see the kinetic model and then the experimental data, we could see some mismatches when the reaction time is small. This mismatch was coming from the hydrated forms of the intermediates. But when the reaction time increased and the HMF conversion becomes around 100%, then we could see that the kinetic model is matching well with the experimental data because all the hydrated intermediate was converted to the alder condensed product. Lastly, we need to find various applications of this new platform chemical. In here, HAH could be converted to a diesel blend stock by hydrogenation and hydrodeoxygenation over metal catalysts such as palladium or platinum tungsten oxide. However, there is an economical challenge to produce diesel blend stock from HAH. The price of HMF is too high for fuel application. So we need to find HAH application in chemical that have higher selling prices. The higher selling price application could be on organic dye. Organic dye must have the high molar excitation coefficient to have a bright color. So we measure the molar excitation coefficient of HAH, and we found that the value of HAH is within the range of the molar excitation coefficient of typical anthraquinone dye. We also switched the UV absorption spectrum of HAH by using the catalytic reaction such as dimerization and etherification. Those catalytic reactions converted the coloring functional groups in HAH and changed the UV absorption spectrum. This tunable spectrum suggested that the color of HAH could be changed by using the catalytic reactions. Lastly, HAH can be used as a monomer for polymer production. The diol functionality in HAH has a reactivity with primer alcohols over an exit catalyst. Also, the central ketone group in HAH was reduced to the secondary alcohol in presence of sodium borohydrate. This reduced HAH can become a cross-linking agent like a glycerol. In summary, we developed an integrated process and produced the HMF at price of $1,300 per ton. This is the cheapest selling price of the HMF. And the HMF can be converted to HAH in high yield by base catalyzed aldehyde condensation. We emphasize that HAH is a promising biomass-based platform chemical with various applications, such as organic dye, monomer, and diesel additive. Thanks for attending my presentation and listening this talk. This work was funded by Department of Energy. I would be happy to take any question about my presentation, or you could ask a question through this email address. Thank you.